This lesson 2 will cover the key static performance specifications that increase value in precision DACs. The objectives of this lesson are to define what resolution and accuracy mean for precision DACs and discuss the differences between both terms. Itemize the error sources that form the total unadjusted error, TUE, and how important it is to have knowledge of the magnitude of this error. It is important to note that the analog output of a DAC can only exist at discrete levels. Resolution represents the number of discrete levels or steps. So essentially, it is the amount by which you can resolve or tune the output of a DAC. Differential nonlinearity is the key specification for resolution. Accuracy represents the quality or closeness of fit of the output to the ideal output. It refers to the difference in the measured output value and the expected value based on a programmed code. And integral nonlinearity is the key specification for accuracy. The ideal step size for each code is 1 LSB, but in practice, each step size is different from its neighbors. A DNL error is defined as the difference between the ideal 1 LSB step and the actual real step as one moves along the transfer function. Step sizes are larger or smaller than ideal due to DNL errors. From a dynamic performance perspective, the effect of DNL error is to add noise or spores to an ideal transfer function. This reduces the accuracy of the conversion beyond the limitations of quantization. A key requirement for a DAC is that it is monotonic. That is, that its analog output voltage should increase or remain the same as the DAC's digital code increases. If the output of the DAC decreases as the digital code increases, a DAC is said to be non-monotonic. Transfer function of non-ideal 3-bit DAC shows DNL and non-monotonicity. In this example, bit 3 is of correct step size and sits at the ideal value. Bit 1, however, is 1 LSB high and increases by 2 LSB instead of the ideal 1 LSB between code 001 and 010. Code transition 010 to 011, which turns on bit 1, is again correct step size, but the actual value remains 1 LSB above ideal. Bit 2, by contrast, is 2 LSB low, and instead of increasing by 1 LSB from code 011 to code 100, the output voltage actually decreases by 1 LSB, and thereby exhibits non-monotonic behavior. The relative accuracy is also known as INL or integral nonlinearity. Integral nonlinearity is the deviation of the actual transfer function from a straight line. Good INL is required for open-loop systems and many closed-loop systems. After removing offset and gain errors, this straight line is a line drawn between the endpoints of the transfer function. Integral nonlinearity results in the addition of harmonics and spores at the output of the system. The type of control application places different requirements on the controlling DAC. In an open-loop application, the DAC drives the load, a valve or an actuator. Due to the lack of feedback, absolute accuracy is critical in keeping the DAC output as close a fit as possible to the ideal DAC transfer function. So selecting a truly accurate DAC is more important in an open-loop system. In a closed-loop control system, an ADC is in the feedback loop controlling the valve or actuator position. In closed-loop applications, DAC resolution is more important than accuracy, as the ADC provides information of any accuracy calibration required. Therefore, less attention is paid to INL. Many people take the worst case accuracy to be the total unadjusted error, and they are correct. It is effectively the worst case the actual output voltage can be from the ideal at any given code. If you program your DAC, you will expect the output to load to a certain value. Depending on your level of experience, you may account for the errors, or you may be surprised when the output voltage or current is not where you expect it to be. If you look at most digital to analog datasheets, you will see many separate error specifications. These sources of error are offset error, gain error, as well as linearity errors. If you want to calculate your overall error specification, in the absence of a total and adjusted error specification, you can use the following formula. As well as the integral nonlinearity, it also accounts for offset and gain errors, or full-scale and zero-scale errors. Full-scale offset error and zero-scale gain error can be used interchangeably in the formula. As stated previously, the formula presented in the previous slide gives the worst-case error in the absence of a total and adjusted error specification. What the previously formula does not take into account is the fact that the worst-case maximum specification of each error component will not take place at the same condition. For example, the worst-case gain error specification might be at -40 degrees with a 3-volt supply voltage, while the worst-case offset error might be at 75 degrees C at 5 volt. If we took the previous formula and inserted the maximum worst-case errors blindly, the worst-case error might look a lot worse than it actually is. Total and adjusted error is all sources of error combined into a single specification. It accounts for the variability of individual worst-case sources of error. This is a plot of voltage versus digital code. It shows the ideal transfer function for a digital to analog converter with the ideal transfer function in red. This is the ideal unipolar transfer function of the DAC, which produces an analog output range from 0 to plus full scale. If we take the worst case INL error, this is the deviation of an actual output voltage from the ideal output voltage on a straight line drawn between the endpoints of the transfer function. It is represented here in blue. We then add the worst case offset error, which is a measure of offset error in the DAC and output amplifier. It is the difference between the actual error and the ideal error. We also add the worst case gain error, which is a measure of the span error of the DAC. It is the deviation in the slope of the actual DAC transfer characteristic from the ideal. Gain error is usually expressed as a percentage of the full-scale range. It is the slope error for the transfer function. We are effectively looking at the calculated worst-case accuracy error we looked at in the first slide. In reality, the worst-case gain, offset, and linearity errors will not usually take place at the same condition. The output may change over temperature. At room temperature, the offset is at its worst, but there is no real gain error. When you look at the same DAC output at -40 degrees C, the offset error might be fine, but there might be a gain error component that is at its worst. When you heat up the part, it may behave with another differing transfer function. If we take a worst case measurement across temperature, as well as process and operational parameters, we have the total and adjusted error. We can see TUE gives a far better indication of the device performance than taking the worst case maximum error sources and adding the values together.